My name is Yasmina Sadna from the University of Batna 2. Today I'll be presenting our work titled Transfer Learning with Enhanced Models for Skin Cancer Detection, a comprehensive evaluation of transfer learning and data augmentation on the AZEC 2020 dataset. This research was conducted in collaboration with Dr. Saliha Mazzouj and Dr. Miriam Khalifa.
Here is the structure. We start with the introduction and motivation, outlining the clinical significance and our research questions. Then, I will detail our methodology, including the dataset, models, and experimental configurations. We dive deep into the results and their interpretation, comparing baseline performance, the effects of augmentation, and our proposed tuned architecture. We'll contextualize these findings with a thorough comparison and discuss model complexity. Finally, we cover the discussion, limitations, and outline potential future work before concluding. Skin cancer represents a significant global health burden, with melanoma being particularly deadly if not caught early. However, traditional diagnosis relies on expert dermatologists. Research often scarce, leading to diagnostic delays, especially in underserved regions. The rapidly growing market for skin cancer treatments, projected to reach nearly 8.5 billion by 2029 as shown in the figure, further underscores the urgent need for effective and accessible diagnostic tools. This highlights the potential impact of AI-driven solutions. Deep learning has shown remarkable promise in automated dermoscopy analysis, achieving performance nearing and sometimes exceeding dermatologist level accuracy. However, training deep CNNs from scratch typically requires vast amounts of labeled data, which is often a bottleneck in the medical domain. So, transfer learning offers a powerful solution by leveraging knowledge from models pre-trained on large datasets like ImageNet, adapting them to medical tasks with scarcer data.
This raises key questions for optimizing transfer learning in dermoscopy. The first one, what is the performance of setting of baseline transfer learning using frozen pre-trained features on the ASIC 2020 datasets?
The second question is, what is the impact of applying standard geometric data augmentation, which is a common practice in deep learning, in the context of dermoscopic image analysis? Does it help or hinder? The third question is, can tuning the architecture by adding some or simple trainable layers outperform the baseline and augmentation methods? So, our main contributions in this work are threefold. First, we conduct a rigorous comparison of four widely used CNN architectures: VGG16, ResNet 50, DenseNet 1-to-1, and Inception V3, across three distinct configurations: baseline transfer learning with standard or geometric data augmentation, and tuned DenseNet or tuned the models, all the models, the baseline models, using the challenging ASIC 2020 dataset. So, second, deep interpretation explaining the surprising failure of standard augmentation in this task and the significant success of simple architectural tuning. Finally, providing practical insights for transfer learning in medical imaging and establishing an efficient, high-performing benchmark with simple tuned DenseNet 1-to-1. Our experiments were conducted on a subset of the ASIC 2020 challenge dataset from CAGO. We used a predefined split.
approximately 10,600 images for training and significant test set of over 7,100 images, allowing for reliable performance assessment. This relatively large test set allows for robust evaluation. So all input images were resized to 256 by 256 pixels. And as you can see from the examples, the dataset includes both malignant and benign lesions, showcasing typical variations in appearance. So in the models used, so we selected for popular CNN architectures, all pre-trained on the ImageNet dataset, known for their diverse designs and proven effectiveness in transfer learning tasks. We have VGG 16, characterized by its depth and stacked 3-3 convolutional layers. We have ResNet 50, introduces residual connections to mitigate vanishing gradients in deep networks. DenseNet 1-to-1, it features dense connectivity where each layer receives inputs from all precedent layers, promoting feature rows and making it highly parameter efficient. As we'll see, this proved crucial. So it's for local information features for it search for details. And Inception v3 employs multi-scale filters and factorized convolutions for robust feature extraction. So it searches for more complicated features, or it's not suitable for medical images, especially in for skin cancer detection. So in experimental configuration, the baseline in transfer learning, our baseline configuration applied standard transfer learning. We used the pre-trained CNN base as a fixed feature extractor by freezing its weights. The original classification layer was removed and replaced with a new trainable head. This head consisted of a global average pooling 2D layer, followed by a 2-unit dense layer for benign and malignant. With softmax activation, only the parameters of this new head were trained on the ASIC 2020 data. The second configuration adds standard geometric data augmentation on the initial dataset. Our third configuration, the tuned architecture, introduces intermediate trainable layers between the frozen base and the final classifier for deeper adaptation. Specifically, we added a conv2 del layer, followed by dropout at 0.5 for regularization, and then a dense layer. These new layers, along with final 2-unit classifier, were trained on the ASIC 2020 dataset. Let's briefly cover the training and evaluation setup. In the training, we used the RM optimizer with cross entropy loss, training for 40 epochs with a batch size of 128 on Google Colab GPUs. We have used the dropout 0.5. In the evaluation, we have using accuracy, precision, recall, F1 score, supplemented by confusion matrix analysis for error types and training validation curves to observe learning dynamic and generalization. Moving to results. The baseline transfer learning performance shows DenseNet 1-to-1 clearly leading, achieving 94.0% accuracy with a strong F1 score and high recall. In contrast, ResNet 50 significantly underperformed at 76% accuracy. So ResNet 50's struggle may because its architecture forces heavy rows of earlier features, which might act as form
of implicit regularization, potentially making it less prone to quickly overfitting the training specifics.
These confusion matrices provide a more granular view of the performance. The training and validation curves are also informative. DenseNet 121 and VGG 16 show good convergence, with validation accuracy closely tracking training accuracy, indicating decent generalization. For Inception v3, however, displays a noticeable gap between its higher training accuracy and lower validation, which plateau earlier. This indicates some degree of overfitting, maybe if we reduce number of epochs, but we haven't a good generalization. Most strikingly, ResNet 50 demonstrates significant training instability, characterized by erratic judged curves for both accuracy and loss. There is also a very large and inconsistent gap between the unstable training performance and the much lower, also unstable validation performance. This confirms poor learning, maybe for the complicated architecture of ResNet 50. So, the surprising failure of data augmentation. When we applied geometric data augmentation, performance decreased across all models compared to the baseline. So why this drop? Our hypothesis, supported by, of course, literature on medical image augmentation, data augmentation, is that geometric transforms disrupt diagnostically critical, often subtle, cues in dermoscopic images, such as lesion symmetry in skin cancer, border regularity, and specific texture patterns. These transformations might introduce more noise than useful invariance for this fine-grained task. So, the power of tuning. In contrast, the augmentation, all the tuned architecture yielded significant performance improvements. DenseNet, for example, reached 96.45% accuracy and 96.50% F1 score. So recall also improved to 96.69%. Other models like ResNet 50 jumping from 69% in the augmented with the augmented dataset, or 76% with the baseline strategy, to 94.07%. And also in the curves, the imbalanced learning rate is reduced. So this table summarizes the accuracy across all three configurations for each model. This bar chart visualizes the comparative accuracy. The blue bars represent baseline, red is for data augmented, and green is for architecture tuned. Model complexity and clinical relevance. Performance isn't the only factor. Model complexity and efficiency are crucial for real-world deployment. This table shows approximate parameters counts. For DenseNet stands out as highly efficient with only around 8 million of parameters. This contrasts sharply with VGG 16, 138 million of parameters, and even ResNet 25.6 million of parameters. For Inception v3, 23.8 million of parameters. It's also far more efficient than large transformer models like VAT-based 86 million, often used in recent studies. We talk about VAT-B0, not B3 or recent, more complicated VAT. For clinical relevance, this makes DanceNet an ideal candidate for deployments, especially in resource-limited settings in the medical use. To put our results in perspective, this table shows a comparison with some other studies, which range from 97% to over 98%. So some of these achieve higher accuracy using large models, ensembles, or potentially different data splits, or pre-processing or maybe optimization techniques. So this slide summarizes key takeaways in our theme. It's important to acknowledge the limitations of this study. We did not include direct comparison with newer architectures, and we only tested geometric transformations. And also, we focused only on binary classification melanoma with non-melanoma. Then multi-classification presents additional challenges. For validation, we used a single train test split, so cathode cross validation would provide a more robust estimate of generalization performance. We didn't employ techniques like GradCam to visualize what the tuned layers learned, which could offer deeper insights and the validations, so we should use other datasets. Our comprehensive evaluation demonstrates that while baseline transfer learning provides a good starting point for skin cancer detection, standard geometric augmentation can significantly degrade performance on dermoscopic images. However, enhancing pre-trained models with strategically added trainable layers tuning effectively adapts features to the domain specifics. Based on these findings, we propose several directions. Extend the approach to multi-class skin lesion classification. To apply explainable AI methods like GradCam to understand the features learned by the tuned layers. And validate our findings more robustly using cathode cross-validation and testing on diverse external datasets. Thank you for your attention. I'm happy to answer any questions you may will have. You can also reach us via the contact details provided.